Now, I covered the first 4 problems on the previous video. I'll cover these 2 and I'll cover the back of this page on this upcoming video. And then on the 3rd video, I'll do the last page of this worksheet. So what is the molarity of the solution that contains 14.92 grams of magnesium oxalate in 3.65 milliliters? Again, we have to be careful with our units of solution. So that's going to be a ridiculously high number, I can already see. Magnesium oxalate. Oxalate has a -2 charge, magnesium has a +2 charge. That part is settled. So I have 14.92 grams of magnesium oxalate. Have to turn that into moles. And that would be, magnesium is 24.3 plus, so 24.3 plus 12 times 2, 24.3 plus 24 plus, that would be 64, which is 112.3 grams for the molar mass of magnesium oxalate. Now my grams cancel out. I get 14.92 divided by 1112.3. I get 0.1329 since I have 4 sig figs here, moles. Now, in this case, it's 3.65 milliliters. If I wanted to do my conversion, 1 liter over 1,000 milliliters, that way my milliliters cancel out, which basically does 3.65 divided by 1,000, which is 0.00365 liters. So I have to put 0.1329 moles over 0.00365 liters. And it's going to be a fairly large number. Which is 36.4, keeping to the lowest number, 36.4 molar magnesium oxalate solution. Okay, so these are fairly straightforward. Now, what mass of lithium phosphate would you, we'll get rid of that word there, we'll say measure to make 2.5 liters of 0.16 molar lithium phosphate. So now in this case, we're working a little bit backwards. Molarity equals moles of solute over liters of solution, which means in this case 1.06, which is my molarity, and that should be italicized, but moles of solute, which we do not know, we'll call that X, and the liters of solution would be 2.5. So if I multiply both sides by 2.5, I end up getting .65 moles of solute, which in this case is lithium phosphate, which has a chemical formula, if you remember, phosphate has a -3 charge, and lithium has a +1, so you need 3 +1s to balance out the -3. So lithium is approximately 7, so that's 21, plus phosphate is 31, plus 4 oxygen is 64, which means I have 52 plus 64, which is 116. So that is my grams for 1 mole of lithium phosphate. I have 2.65. The question is asking what mass of lithium would you need to measure? So 2.65 moles times 116 grams over 1 mole, because I want to cancel out my moles this time and get the grams. So I do that times 2.65, which is 307.4 grams. However, looking up here, I have 3 significant digits, 2 significant digits. I'm only really allowed to have 2 sig figs in my final answer, which means that would be 310 grams of lithium phosphate. And I hope that fits on the bottom. Yes. Okay. Let me turn the page and get it balanced. Now, starting with number 7, if you evaporated 250 milliliters of a 3.5 molar solution of iron 2 nitrate, what mass of iron 2 nitrate, what mass of iron 2 nitrate would you recover? So again, I already know my molarity there, 3.5, and then that equals X, because I do not know the amount of my iron 2 nitrate, X over 250 milliliters, which would be the same thing as do my conversion, so I cancel out milliliters. 0.250 liters. So multiply both sides by, so I get 3.5 times 0.250, 0.875, X equals 0.875 moles of iron 2 nitrite, which would be Fe. Iron has a +2 charge in this case. I need 2 nitrites in order to balance it, because nitrite has a -1 charge. Okay, so now I need to do the gram molar mass of iron 2 nitrite. Iron is 55.8 plus 2 times 14 is 28 plus 4 times 16 is 64. So that is 55.8 plus 28 plus 64. Fairly big formula unit. 147.8 grams over 1 mole. So that would be 0.875 times 147.8, 129.3. Let me just check to make sure my answer matches. So the only thing, if I did get 129.325, I have far too many significant digits, which that would be in grams, but I need to convert this to the proper number of significant digits, which is 2. Actually, in this case it has 3 significant digits. This case it has 2. I have to do it to 2, so that would be 130 grams of iron 2 nitrate. Okay. A chemist has 4.0 grams of silver nitrate and needs to prepare 2 liters of a 0.01 molar solution. Will there be enough silver nitrate? So first, we need to figure out how many moles we will be dealing with, although it might be a good idea to first deal with the grams of silver nitrate. Grams turning into the moles, that's always a good first step. So 4.0 grams times 1 mole over the gram molar mass of silver nitrate, which is AgNO3. Going to my trusty periodic table, silver is 107.87. Plus 14 for nitrogen, plus 3 oxygens is 48. That means 107.9 plus 14 plus 48 equals 169.9, basically 170. Okay, so 4 grams up here, 169.9 grams. That way my grams cancel out. 4 divided by 169.9 equals 0.2354. So keeping in context and keeping in the idea of how many significant figures really doesn't matter at this particular moment, but I would have 0.02354, let's say, moles of silver nitrate. Now I have to figure out how many moles would I need to make 2 liters of a 0.10 molar solution. So I go 0.010 molar solution equals X over 2.0 liters. Multiply both sides by 2.0. I end up needing 0.020 moles of silver nitrate. You can see I clearly have that. Now the next step is it's saying how much silver nitrate would be left over. Will there be enough silver nitrate? I have this much. I need this much. I definitely have that much. But then the question is how much silver nitrate will be left over? So what I could do is I change this back into grams, or I could just subtract this from this and go back to grams. So why don't I do it that way? I need this much. I have this much. 0.02354 minus 0.02000 equals 0.00354. 0.00354 moles are left over. Now I take that, it doesn't say how much and what units, but if I wanted to change that back to grams, I would do 169.9 grams over 1 mole. So my moles cancel out, and I get 0.00354 times 169.9, which equals 0.60 grams remaining. 0.6 grams remaining. In order to make this, if I plug this number in and change that to grams, I get 3.4 grams are used to make this solution, and then I would have, since I started with 4, I would have 0.6 grams remaining. Okay, I will finish this one and then I'll stop for this last one, which is a limiting reactant problem. I'll complete this one and then I'll make one final video. So, George pours 500 milliliters of a 3 molar solution sodium hydroxide into a 2 liter volumetric flask and fills the flask up with water. What is the new molarity of the solution? So this is actually a dilution problem. This is not a straight up regular molarity problem. The formula for dilutions is M1V1 equals M2V2. So in this case we have 500 milliliters of a 3 molar solution. So 3.0. Now it actually doesn't matter whether I choose to use milliliters or I choose to use liters. However, I can't put 500 on one side and 2 on the other. I have to make the units consistent. So in this case, 500 milliliters is the same as 0.50 liters, and this is molarity, equals X, which is my new molarity. It says, what is the new molarity? I don't know that. The new volume is 2 liters. Okay, so on both sides, I have 3 times 0.5, which is 1.5, divided by 2 equals 0.75. So X equals 0.75. What was X's value? It was this M2, the new molarity of the solution. So the new solution is 0.75 molar sodium hydroxide. Okay, I will stop it here, and then I'll do the final video about limiting reactant. And I just realized that I cut that bottom part off a little bit. So hopefully now you'll be able to see what I did. M1 V1 equals M2 V2. I explained that. So my M1 is my 3 molar. My 500 milliliters turns into 0.5 liters. My new volume, V2, is 2. I had to solve for X, which is the new molarity. So all I did was I had 3 times 0.5 is 1.5. 1.5 divided by 2 is 0.75. That 0.75 value is X, which is my second molarity. The new solution's molarity is 0.75 molar. Okay, with that, I will now stop and I will make the final video about this limiting reactant problem.